¿Qué tal? ¿Qué tal? ¿Me oís bien ahora? ¿Qué tal? ¿Alguien puede responderme? ¿Me oís bien ahora? ¿Va la cosa bien? ¿Va la cosa bien? ¿Me recibís ahí? Can you hear me now? Can you hear me now? Yes? Can we start? Can we? Yes? Thank you. Thank you. I want to try to do this class, and please pay attention now. Stop chatting now. Stop chatting. So remember, we're going to work about the magnetosphere, and all you need to have before you is your note, your social science note. We're going to start with doing the review about what a magnetic field is, and then we're going to explain the magnetosphere, a very interesting theme, an awesome theme. And now, as you know, a magnetic field is the area where a magnet can exert its magnetic force. Okay? And this is an invisible zone that extends all around the magnet. Okay? And conventionally means that actually is not true. Okay, but all of us came to an agreement about that. So conventionally, the magnetic field lines go from the north to the south pole, and I remember you that in Spanish, the north pole is the positive pole, and the south pole is the negative pole. In Spanish, we don't have a north and a south pole in a magnet, okay? Nor in electricity. We have a positive and a negative pole. And in English, they say north and south pole. And magnetic fields can penetrate through all kinds of materials, not just air or paper. Very good. And you had to do some exercises the other day about the magnetic field. The first of them was the number 3. So you have to draw the magnetic field in the diagram. You have here a magnet. You can see it, North Pole here, up, and down you have the South Pole. And these lines are the lines you have to complete. This is the magnetic field. Okay, and it goes from North Pole all the way to the South Pole. Okay, both directions. Both directions. This is interesting. Okay, and then you have there kind of text about explaining magnetism, and it reads: Imagine a factory somewhere that makes little magnets and ships them out to schools for their science lessons. Picture a guy called Dave who has to drive their truck, transporting lots of cardboard boxes, each one with a magnet inside it, to a different school. Dave doesn't have time to worry which way the boxes are stacked, so he piles them inside his trucks any old hole. That means in any order. In any order. The magnet inside one box could be pointing north, while the other next to it is pointing south, east, or west. Overall, the magnets are all jumbled up so in a disarray. In a disarray. In disarray. And even though magnetic fields leak out of each box, they all cancel one another out. This is the picture. It describes the way in which this guy, Dave, arranged these boxes. You can see this is the magnetic field of one box, this is the other, and they are neutralizing each other. Okay. But the same factory employs another truck driver called Bill, who couldn't be more different. He likes everything tidy, so he loads his truck a different way, stacking all boxes neatly so they line up exactly the same way. Can you see here? You see here? Same way. The magnetic field from one box will align with the field from all the other boxes, effectively turning the truck into one giant magnet. Okay, so the cab will be like a giant north pole, and the back of the truck a huge south pole. So you have to imagine in Bill's truck, this is the truck, this is the cab. Okay, this is the north pole of the cab, and this is the south pole of the cab. So the difference is that in Dave's truck is no magnet at all, because all boxes are neutralizing each other, and instead in Bill's truck, the whole truck is like a giant magnet. And these are the questions. So what's the difference between Dave and Bill arranging the magnet boxes? One of them is, I think it's Dave, arranges all these boxes in disarray, in no order at all. So, and Bill's truck is a truck in which all boxes are in the same way arranged. And number two, how are finally the magnetic fields in Dave's truck arranged? In a disarray, in no order at all. And in Bill's truck, number three, in the same order. Number four, magnetically speaking, what happens in Dave's truck? And the answer is that there is no magnet at all. And in Bill's truck, the difference is that in Bill's truck there is a giant magnet. Very good. So, and number five, very easy. All of you did it correctly. So write attract or repel under the correct pictures. And you have here two magnets. This is the North Pole, the red one, and this is the South Pole. So the North Pole is pointing to the South Pole and the other way around. So as a result, these two magnets attract each other. Okay. Conversely, you have here the two magnets. This is the South Pole, is pointing to a like pole, another South Pole, and the North Pole, another North Pole. So the result is that both magnets repel each other. Very good. So now go to the magnetosphere, and to do that, I'd like you to watch a documentary, a very interesting documentary. So, as I told you yesterday, if anyone is interested in any of these clips, please let me know. Pay attention.
Earth itself is a huge magnet. This animation depicts Earth's magnetic field lines as viewed from outer space. This is Earth's magnetosphere. Its magnetic field is similar to that of a bar magnet. But you'll notice that the field lines far away from Earth, they bend away. This is due to the ionized solar wind from the sun that encounters Earth. As we discuss elsewhere, Earth's magnetosphere acts as a shield, protecting us from this energetic solar wind. The source of Earth's magnetism is still not completely understood. Most investigators, however, attribute the field to convection currents within Earth's interior. What we do know is that the direction and strength of Earth's magnetic field changes over time. Let's explore this. First, If you hold a compass at either Earth's north or south magnetic pole, the needle would face vertically, straight up and down. Earth's magnetic pole is located where the magnetic field lines are perpendicular to Earth's surface. Earth, however, it's a complicated and rather dynamic planet.
Take a look here. Take a look here. So this is the geographic North Pole. In this case, this is the magnetic North Pole. Not always. Sometimes this is the magnetic North Pole, and sometimes this is the South Pole. It changes, okay? But it's very difficult for them to be in the same point. To be in the same point. This is interesting, very interesting.
Because of this, the magnetic poles are not necessarily fixed at the same location. We find that the magnetic poles tend to wander. Here's a map showing the location of the northern magnetic pole over the past few centuries. As of 2020, the Earth's magnetic pole in the northern hemisphere is slowly moving on a path from Arctic Canada to northern Siberia. As shown on this magnetic declination map, the magnetic field lines along Earth's surface don't always point to the magnetic poles. This map is useful in navigation to show how far off your compass is reading from the geographic pole. Of course, because Earth is a complicated and dynamic planet, these declination maps always need to be updated. Today, however, navigation is done primarily through our network of global positioning satellites, also known as GPS. Now, zoom out to a planetary point of view, and you'll see the field lines appear to merge at a location that is actually different from the magnetic poles. This broad-scale view of a magnetic pole is called the geomagnetic pole. I know. Geomagnetic pole sounds an awful lot like magnetic pole, but there's a difference. The magnetic pole is located where a compass points in a direction perpendicular to the surface, straight up and down. The geomagnetic pole is like the average of all the variations found across the planet. It's what ions from outer space encounter, which is why the aurora are generally centered about the geomagnetic poles. The northern geomagnetic pole is currently somewhere over Ellesmere Island in northern Canada, which is different from the location of the magnetic pole, which of course is different from the geographic pole. Here's another fun fact. The geomagnetic poles are not currently aligned to the geographic poles, true, but over thousands of years, they migrate around the geographic poles. Average out the positions of the geomagnetic poles over thousands of years, and you'll find you've got the position of the geographic pole. Well, that's interesting. Even more interesting, the magnetic poles sometimes flip orientation. North becomes south and south becomes north. How do we know this? The most direct evidence comes from ocean seafloors. As parts of the floor spread apart, metal containing molten rock solidifies and thereby captures the orientation of the magnetic poles at that time. Studies of the ocean floors show bands where the magnetic orientation of minerals making up the floor are flipped in the same way on opposite sides of the ocean ridge.
This is a picture of the bottom of the ocean, okay? And in the bottom of the ocean there is a ridge by which a lot of minerals are coming out from the mantle of the earth. And this is the phenomenon that changes the orientation of the magnetic field. And it makes sometimes that's where the North Pole, the magnetic North Pole is, changes the other way. This is interesting. You had to sail, you had to drive to sail on a boat. You need to know all of that. And people and scientists that are making satellites there, okay, with GPS, need to know all these kind of things. So there are many occasions in which our devices didn't work because of that.
This allows us to date the timing of magnetic reversals. The last one occurring about 700,000 years ago. But does the magnetic field disappear during a reversal? Geologic records show that past reversals have had no significant impact on life forms. This suggests that while the magnetic field might weaken during a flip, enough remains to deflect solar winds. Geologic records also show that a reversal only takes hundreds or thousands of years to occur, which is rather quick on geological timescales. The next magnetic reversal, it could happen any time. But for now, you can rest easy in your appreciation of Earth's dynamic magnetic field. Good energy.
Good, good. Now with that in mind, go again to your text part. So this is the magnetosphere. These are the invisible lines that are protecting, that are surrounding the Earth. Okay, good. So, so the magnetosphere. We know that our planet has liquid iron in its core. This is the reason why we are in a giant magnet. The Earth is a giant magnet. Why is it? Because in its core there is iron there. Not only iron, iron, nickel, but iron is the most important metal here in the center of the Earth. And not only that, the Earth is revolving around itself. So this is the rotation that makes the magnetosphere, that makes the Earth to turn into a giant magnet. Rotation movement turns the Earth into a giant magnet. The Earth's magnetic field is called the magnetosphere. So the magnetosphere is the name that is given to the magnetic field of the Earth. It stretches out into space and affects things around it. The magnetosphere protects the Earth from the solar wind. Solar wind is a kind of wind made of protons, okay, and it affects the Earth. Thanks to our magnetic field, we have life on Earth. Okay, this is totally important for life on Earth. The magnetic field is also useful. This magnetic field of the Earth is also useful to animals such as birds and whales, who use it to find the right direction when migrating. We don't know why. We don't know why, but even when they are baby birds or baby whales, they know exactly the way in which they had to go, and this is because of the magnetic field of the Earth. They are sensitive to the magnetic field of the Earth. However, the geographic North Pole is roughly the magnetic South Pole and the other way around. Okay, and not only this way. And sometimes that the North Pole, the geographic North Pole, is very near the magnetic North Pole, and the other way around. This is moving, this is changing the whole time, and that's why the North Pole of a compass points to the geographic North Pole of the Earth. Okay, and then you have here an exercise number 7. Although you did it, we're going to correct it. So 7.1. What is the metal in the Earth's core? Metal. There are two important metals. The most important is iron. Iron. Remember that objects that are made of iron are objects that are magnetic object, not magnet, but can be magnetized. So number 4. Why is the Earth a giant magnet? The answer comprises two things. One of them, because in the core, the nucleus in the core of the Earth, there is iron. And the second thing, because the Earth is revolving around itself. The two things are necessary. Not only one, the two things are necessary. And are the Earth's geographical and magnetic poles the same? No. No. Sometimes they can be very near one to the other, okay? And there are times when the geographic North Pole is the magnetic South Pole. Okay? Now, for this is interesting. What are cosmic rays? Is the solar wind cosmic rays? Solar winds. These are winds that carry protons, so positive charge. If they impact on the Earth, all life on the planet will disappear. So thanks to the magnetic pole, the magnetic field, the Earth can't have life. So, number 5. Where do they come from? The cosmic rays. The solar wind, so they come from the sun. Good, very good. Number 6. The North Pole of a compass points to the Earth's North Pole. Why is it? Why is it? Because the North Pole is attracted by the South Pole. Okay, so there are many times in which the North Pole is pointing out to the south magnetic pole. Number 7. Why is the magnetosphere important for humans? For us? Because, first thing, we can live. And second thing, we know enough about magnetism, we can orientate ourselves there in the Earth. And number 8. Why is the magnetosphere important for some animals? Put an example. Animals, many migrating birds use the magnetosphere to orientate themselves. Okay, not only migrating birds, but also whales and many other animals. We don't know why. Very good. Now I'd like you to watch two other interesting video. I don't know if we have enough time. So, and this is about the magnetic shield of the Earth, how the Earth is protected by its magnetic field. So pay attention. We don't have time to see the third one, so we want to make the most with this. Pay attention.
Our sun is constantly blasting huge amounts of hot plasma out into space. All those charged particles have a big effect on everything in their path. So what's protecting Earth from the solar wind and solar storms? Earth's thick atmosphere provides some defense, scattering and absorbing solar particles before they reach the surface. But our planet also has a secret weapon, a strong magnetic field it projects into space, mostly generated by molten iron alloys moving in Earth's outer core. The area
This shape is the magnetic field that is deflected, because here, this part, you have to imagine the sun, and this is the direction of the solar wind, okay? And as the solar wind blows, this is the deflection of the magnetic field of the Earth.
of space where the magnetic field interacts with the solar wind is called Earth's magnetosphere. Its shape constantly changes as it's bombarded by solar particles. As positively charged protons and negatively charged electrons enter the magnetosphere, most of them are deflected around Earth, long before they reach the atmosphere. The magnetosphere really gets tested when big solar storms, carrying more plasma and traveling at higher speeds, are on a collision course with Earth. While most of the plasma is deflected, some of it gets trapped in the magnetosphere and funnels back toward Earth along field lines emanating from the poles. As charged particles from the Sun collide with nitrogen and oxygen molecules in our atmosphere, they create the cosmic light shows known as auroras.
This is this is called in Spanish una aurora boreal. In English, aurora borealis. Okay, this is beautiful. You can see this phenomena if you are very near the North or South Pole. Okay, in countries such as Finland or Norway, you can see them all nights.
The bigger the storm, the further from the poles auroras can be seen. Some storms are so big they interfere with satellites, cause planes to alter their routes, and can create other problems. The vast majority of the time, these inconveniences are pretty minor. But the next time the solar version of a perfect storm overwhelms Earth's magnetic shield, we might not be so lucky.
So, thanks to the magnetic field, the Earth is not burned at all. Good, very good. And now go please again to your exercise part. And you have here text. We're not to read it because we don't have time now. And this is an exercise that reminds you to the solar system. Okay, you know this is the Sun, this is Mercury, Venus, this is the Earth, the blue planet, the Earth. Okay, we're living here, the Earth. This is Mars. These four are called the rocky planets. Rocky planets because they are made of rocks. Rocks. Okay, and these other planets are called the gas planets. This is Jupiter. This is Saturn, as you know. This is Uranus. This is Neptune, I think. Uranus is Neptune. This is Pluto. Okay, so these are the gas planets. All you have to do is to classify from 1 the strongest to 4 the weakest according to their magnetic fields. We don't have time now to do that. Good. Now for today, remember you have to read point number 2, electricity. Okay, on your own. So next week we're going to explain it. But today you have to read it. You have to underline all keywords you can find here. It's interesting, and you have to stop here in the static electricity. Okay, this is a very interesting thing. And when you do that, try to go to the next exercise. Electricity. You have to answer number 9. Exercise number 9. Remember, and exercise number 11. Okay, there's a mistake of mine. There's no number 10. Okay, and you have to complete the gaps in this text. Okay, with these choices. Good, very good, and I think this is all. Okay, very good. So now we are leaving, and in just 20 minutes we see ourselves to do maths. Thank you for your attention and sorry for these technical mistakes. See you.